Hello and welcome to the third part of the series. Today we are going to post-process an OpenFOAM case using Meta. The post-processing will include the creation of cut planes, streamlines, ISO functions, the generation of a report, and some insight on how you can automate this process. Let's jump into Meta now. First thing we need to do is to read the model and some results. We will do so using the template manager. Have in mind that when dealing with an OpenFOAM case, we will read a directory and not a specific file. We can load results now. The static pressure, velocity magnitude, lambda2 criterion for the identification of the vortices, and some pressure coefficients. Let's also read all available vector results. By default, Meta will select to read results from all states, but actually we want to read only the last state. This is a steady state simulation. So we can deselect the rest and press read and wait a couple of seconds. Now the results are read. The geometry is here. Let's have a look. Let's select now the scalar results from the scalar button. Of course, we need to move first to the first state. There's also the zero state, the initial conditions. But in order to visualize the results, we need to move the bar to state 1. By using the right click on the fringe bar, we can change the min and max values based on custom values that we want. We can also activate the wire in order to visualize the mesh. We can change the visualization based on how the results will be plotted, on nodes or on elements. You can see how much smoother the visualization is on nodes, since an averaging of neighboring values is taking place. There is the normal plot, the contour plot that will separate areas based on their values, or a combination of normal and contour plot. We can also change the palette colors of the fringe bar in order to color only the extreme values of the result. So we can put some gray colors here and have only the palette showing the extreme ones. Additionally, there's the option to put tags, names, on the values, on some of the values. So here I can write max, for example, and min. And this will replace the values in the fringe bar. Or we can even change the colors of the fringe bar. We can add some, remove some. So I will make the fringe bar more analytic, and I will also reset the numbers by removing the names that I've put before. Let's activate back the auto scale in order for Meta to calculate the min and max values. And we can change the scalar results. So what we see now is velocity magnitude. Actually, the velocity on the walls, everything is 0. That's why everything is blue. A part of the moving walls, as we can see here, like the disc brake and the tire. However, there's another option that we can read any scalar result, like now the velocity magnitude, by reading not the wall value, but actually what is on the first cell, the value that is on the first cell, the first layer. We will read it now using the standard read results and not the results template. And as we can see here, the coloring is proper based on the first layer value. We can change again the min and max values and the visualization on node using normal and contour line plot. Another interesting functionality is the user field function tool, where you can calculate a new field. And now what we're going to do is we will normalize the velocity magnitude with the free stream velocity. So we will use the state 1 velocity magnitude and divide it with 40 meters per second, which is the free stream velocity. The new result is now displayed. We can see it also selected at the scalar selection bar below. And if we give the proper values now, like 1 and 0, we can see the proper coloring. Let's switch back now to the normal plot visualization. This is a nice contour plot since it shows clearly where we have acceleration of the flow. Moving on now, what is really good to do in order to maintain a consistent way of post-processing is to define custom views. To do so, we'll go to Views, and here there are already defined some default views, based of course on the orientation of the global axis. And by using the Add button, the user can create custom views, or can even import them. Let's define a name now in the custom view, like upper left. And let's do the same for the opposite side. Okay, it seems good. Another cool feature is that you can change the lighting. You can open settings and the user has the option to activate more lighting sources or edit the intensity and the position of the current light. Moving on, since we are modifying the fringe bar range a lot, let's see how we can save a custom range. We can right-click on the fringe bar, activate the non-linear spacing, and here we can edit the values, and we can also give a name at this custom spacing. Press the Add button, and now this custom spacing is saved, and it can be accessed later on when it's needed. from the same place. Now let's activate again the auto range, and let's bring another scalar, which will be the lambda2 criterion, in order to build some isosurfaces. Let's create and select new default value, give a name to the isosurface, and this will run on the active scalar result. So now lambda2 is active, and with a value of -1000, we can identify the vortices around the model. If we deactivate the scalar, we see that the ISO function is colored green by default, and if we enter into the ISO function menu, we can see that we can select the scalar that will run on. So it's not the active one now, it's always lambda2. And now if we activate the scalar that we have selected total pressure as an active scalar, the coloring is based on that. So the ISO function is created based on lambda2, but the coloring is of the active scalar. We can change the scalar range from 1000 to -1000, and we can also change the model coloring based on the ANSA part, for example, just to have a uniform color instead of the property coloring. And in this way we can see clearly the ISO function drawn and colored based on the total pressure. This is a very useful feature, since we can not only see where the vortex structures are, but we can also see how much energy they transfer. Let's see some more options now. We can hide the value of the ISO function. We can also deactivate the scalar fringe, and let's apply some transparency. And we can also remove the feature line by setting the width to 0. This is just an alternative for the visualization, nothing much more. And let's see what else we can do with the ISO functions. We can use the ISO function in order to enclose the wake inside the ISO function by using a new closed upper ISO function at total pressure. So what we will do now is create an ISO function that will be a closed volume, and this later on can be output as an STL and can be imported in ANSA in order to use this closed volume as a refinement area while building the mesh. While we do that, let's also overlay results of the velocity magnitude on the ISO surface for visualization purposes. And then let's hide all the PIDs of the car, just to showcase that this is a closed volume separated by the ISO function. By pressing all, have in mind that not only the PIDs come to visible, but also any cut planes, streamlines, or ISO functions. So use that carefully, because on a big model it will cause a delay. And now it's time to have a look at the cut plane functionality. Let's create a new cut plane oriented normal to the x-axis. And let's edit the position now by selecting the cutting plane, press edit position, and drag it, keeping the middle mouse button pressed. As we see now, the model is clipped by the cut plane. Let's change that. And let's also change the height and length of the cut plane by activating the grid, which we can manually change. And then we will switch from an infinite plane to a finite one. In order to be precise, we can change the min and max values in order to have a purely symmetric cut plane. And we can activate the finite plane flag. Now it's obvious that the plane has been restricted at the boundaries of the grid that we modified. Let's also have a look now at total pressure and how it is drawn on the cut plane. And there's another cool feature that if we change first the range and we set it in a rather small value, so that the max, the values around the cut plane exceed the max value, it's nice now that we can change the transparency of this color at the max value. So everything is transparent apart of the values below of what we've set as max. Let's create now some cut planes at the back by duplicating one plane. And in this way, the settings remain the same, and we just need to move it at the distance we want. Let's do this a couple of times, and we'll have a nice visualization of how the flow behaves at the rear of the car. In order to be precise and consistent, let's change the origin of the planes in order to make sure that the distance between them remains the same. Let's mark them all now, and let's go to the Fringe tab, activate the LIC style, and set a scale of the line integral convolution visualization. The lower this value gets, the higher the accuracy. However, there's a limitation from the GPU RAM available on our machine. This is a nice trick to visualize the vortices on the planes. Relatively easy. And if we overlay this with what we had created before, the ISO function of the lambda2 criterion, we can see that there is a good match of where the vortex structure is and where it is located on the cut plane by the LIC visualization. Let's hide now the cut planes and create another one, normal to the y-axis. Let's clip the model by plane. And let's also bring back all the colors, remove the transparency, change the range limits according to the pressure coefficient result that is active now. We will again activate the grid in order to make a finite plane smaller than the current one. Because this plane now is going to be used for a 2D plot, and we will see right away how. Let's move it into position. What we would like to do now is to have a cut plane slicing the front element of the front wing, and then we will use this cut plane to identify the section exactly and plot in a 2D plot the pressure coefficient around the wing. Okay, now the positioning is finished and the cut plane has the correct size. Let's right click and select plot section. Here at y-axis we will select the scalar and press OK. And we get the 2D plot of the pressure coefficient around the section of the front wing. Let's tile the two windows now and do this interactively. A very useful tool to study the pressure distribution at cross-section of wings. We can now create some more cut planes in order to visualize the flow in another frame vertical to the z-axis. This time we do not want to show the model or clip the model, we just want to visualize the cut plane only. Let's edit the origin by typing the correct number that we want, so that we place the cut plane at the height we wish. And here, let's select now mode visibility slice. And slice width, we will type 0, so only the cut plane will be visible. Let's switch the scalar result to total pressure coefficient and change the range from 1 to -1. And this is another nice section plot that we could include in our report. We can quickly change the height of the cut plane at the origin and examine different areas of the model, as well as different scalar results. In order to make it a little more fancy, let's switch now to velocity magnitude and also change the height to enter the region that has high flow phenomena at the wheel. And let's activate also the LIC style. We will edit the scale a bit in order to refine as much as possible the convolution visualization. If we drop more than this value, it will exceed the GPU memory, and we cannot further improve the visualization. But there's a trick that we can do in order to save some memory, and this is to make a finite plane. So we will activate the grid again, change the boundaries of the cut plane, and activate the flag that says that from now on this should be a finite plane. And now we can drop down to 0.006 without getting our memory filled up. Let's create on the fly two more cut planes with LIC visualization to check the flow close to the wheel. Once more, we need to make the plane finite, so we adjust the grid, and then we're going to move it into position and enable the LIC style. The process is familiar by now, so for the second plane, let's jump right at the result. So the finite cut planes along with LIC visualization give us a pretty good indication of how the flow is resolved around the wheel. What is also relevant to be mentioned here is the statistics tool. We will resize this cut plane to fit the gap between the elements of the front wing, and then use it for our calculation. Now we will open the statistics tool, remove all the default entries, and use the cut plane as a reference to measure the mass flow that passes through. Let's remove the columns that are not needed. And let's calculate now the mass flow rate that passes through the cut plane. There are many integral functions that can be used on plane, size of actions, PIDs, etc. These integrals can be also calculated through the PID list when they refer only to PIDs. As we see here, there is area weighted average, mass weighted average, mass flow or volume flow rate, and even forces and moments. And let's move now to the flow paths, which is also a very useful tool. Let's switch to PID view and then activate the flow paths and create a new streamline set from plane. Let's orient the plane now. We can edit and then orient it towards the x-axis, and also by pressing the middle mouse button we can drag it to change the position. Click twice on the edges of the plane and we can resize it. The first click will select the edge, and the second is used to drag it. What we would like to see now is actually how the flow behaves at the cooling duct of the disc brakes. So we will resize the plane in order to fit at that location. Let's hide some PIDs in order to make it easier. And now we are good to go. We can open the Streamlines menu by clicking on the icon, and here let's activate the shade from the styles in order to visualize the streamlines with thickness. We can also, from the Edit tab, change the number of the streamlines in both S and T axis. Then we will set the direction as both in order to create streamlines both upstream and downstream. Let's activate the fringe color so the streamlines get colored by the actives color. We can change now the actives color to total pressure and set the auto range on at the fringe bar. In this way, not only we visualize how the air is moving, but we see the energy that is being transferred. Let's make now some PIDs transparent in order to see the flow inside. This can be done by activating the transparency button and setting there the desired transparency number as a percentage, and then clicking on the PID. Now it's much easier to see how the flow behaves inside the cooling duct. And let's make a small difference by changing the fringe bar into a horizontal one this time. We can change to perspective view mode, and this is another cool image that we could include in our report. Moving on, let's hide the streamlines and remove the transparency. And let's create now another plane of streamlines. I will change the orientation to the x-axis, and I will also move it to place it at the correct location, change the number of streamlines, and we will activate again the shade and the fringe coloring. At the animation tab, we will activate the animate flag, and we can also control how the segmentation of the streamlines will be done by changing the internal coverage percentage. The animation can be recorded in AVI, MP4 or other formats, and can be placed also inside the report that we're going to build. Another nice feature is that we can modify the visualization of each PID through the PID list. In this way, the results can be customized for different areas of the model. So we open the PID list and we select the desired PIDs. Then we activate the results that we want to show. For example, we can have total pressure scalar results for the car body, LIC visualization for the front wing along with scalar results, vector results for the tires, and some transparency for the rims. So drawing styles, fringe styles, vector styles, LIC or even rendering can be affected per PID. We can also switch on perspective view mode for a more realistic view. So there's another nice view to create images for our report, showing areas of recirculation and separation. By pressing F1, F2, F3, we can change views based on the global axis orientation. Moving on, we can have a look at a handy tool that can help us create a cool animation. The animation editor takes snapshots of the model and links them in a smooth animation. Here, streamlines, cut planes, and ISO functions can be included. Let's try this small animation of 3 keyframes and see how it looks. By changing the subframes into a bigger number, we will make the animation smoother. Let's do that for all keyframes. Let's include some cut planes in the animation. When activating the visibility of the cut plane, we can see that automatically there is a meta command printed on the bottom left. This command can be used as a keyframe command in order to be executed when this keyframe is active. In this way, we can hide and show planes, hide or show streamlines automatically. So keyframes are actually snapshots of the model. If we want the animation to spend more time in one specific view, we can add more keyframes without moving the model. Let's hide now the plane so we can copy the meta command and place it as a keyframe command. So while the animation is run, the cut plane will be shown and then it will be hidden automatically on different keyframes. This is an iterative process. We need to make sure that the animation will be run smoothly. So many things are trial error. Let's create some streamlines that will be used as an animation inside the animation editor. So the animation of the streamlines will start when a specific keyframe will be executed from the animation editor. Once more, let's change the visualization of the streamlines to be more pretty. And let's keep the flag of the animation active because then this is needed to be run from the animation editor. We also need the command of showing the streamlines, so let's copy that as a keyframe command. We can continue adding keyframes, and at a specific keyframe we can switch to the Streamlines tab and select the streamlines that we want to animate. Now the streamlines will be animated for some keyframes, so we need to add more keyframes after the animation has been started. Let's add more keyframes, and let's also change the result to velocity magnitude. We can copy this as a keyframe command, and let's also change the range. That again, we can use the meta command and place it to be changed automatically. So we will start the animation with the total pressure visualization as a result, and then it will be changed automatically to velocity magnitude. So let's preview the animation now. The preview of the animation seems good. Have in mind that while we preview the animation, the commands are run simultaneously. So the result is changing, the fringe bar range as well, and the cut plane is hidden. In order to rerun the animation, we need to initialize those actions and then record it. So I have initialized the model, and now we can record it. Let's have a look now at the recorded session of the animation. I'm quite pleased with the result, and let's move on. Finally, let's start creating a report. There's the Report Composer tool in Meta, which helps the user create a presentation in PBTX format, among others. This can be later on edited in PowerPoint. Snapshots of the model can be taken by just drag and drop. So this is quite easy, filling a report. So let's spend some time to do that. Now I'm using the default views that are saved inside Meta using F1, F2 buttons. But of course we could also use the custom views that we saved at the start of the session. However, something that we need to include in the report is forces and coefficients. So we can use the CFD post toolbar for the calculation. The reference values can be read directly by the OpenFOAM directory, or the user can set them up. Meta can also measure the frontal area. This can be done if you properly orient the model facing the screen. Since it is a pixel-based method, proper orientation is vital or you will get wrong results. Let's include this table of forces and coefficients in our report. We can include, of course, the animation we created from the animation editor. Now it is time to create our cover for the report. We can click on the rendering icon and click again using the right mouse button to open the materials list. We can assign different materials per PAD to give a more realistic feel to our model. Apart of the materials listed here, Meta can also read external libraries of materials, or the user can specify his own custom materials. Finally, let's bring a background image and fit the model, showing some streamlines as well. We can auto-scale the image in order to fit properly to the model. Let's select as a result for the streamlines to be colored based on the pressure coefficient. Adjust the range accordingly. Let's change the number of streamlines. We can hide the fringe bar. And we're ready to capture the cover image. Maybe some small adjustments at the lighting. Let's put this image now first and drag and drop. The report could be now completed using views from the cut planes, ISO functions, and streamlines that we created previously. All the actions done are automatically recorded by Meta. They can be seen using the session editor. We can edit them, add more or remove some, and create a session that will automatize our process. We can also copy commands, as we did for the animation editor, and use them to create a new session. The session commands can be coupled with a Python script in order to further expand the capabilities of the post-processing automation. Here we conclude the webinar on the post-processing using Meta. I hope you enjoyed the session and that you will be able to apply some of the knowledge gained today. Thank you for watching.